Hello, I've been making a series of videos lately on the Blackpool Tower. I think I'm going to put a card or leave a link or something to the playlist that has all of these videos. And I didn't think that I was going to be making this video, but it was because I had a discussion with a flat earther in those other videos that led me to think that either this flat earther is a troll and trying to get under my skin, or that person is extremely dense and doesn't get it at all, regardless of how many times I tried to explain it. And I kind of think maybe it's the latter, although I wouldn't be surprised if it was a bit of the former. Anyways, this is going to be a wrap up of my Blackpool Tower series, the Crayon edition. In the discussions, there were a couple of things that came up. Mainly, the Rayleigh criterion has been brought up time and time again, and their excuse for using it is that it allows them to justify why part of a mountain is hidden behind the curvature of the earth, or why the bottom of a boat is cut off. If you read what the Rayleigh criterion really means, it doesn't mean anything like that. All it means is that below a certain point, two objects that are adjacent to each other tend to blur and blend together as if it was a single object. That's really all it means. And I'll get back to that in a little bit. And of course, the other one was this person kept asking me on a number of occasions to define geometric horizon. And in my case, what I was doing, the geometric horizon is entirely moot, and I will show that shortly. But first, time to bring out the crayons. So there are two basic models floating around. There is the well-established and well-understood oblate spheroid globe Earth that lives in a heliocentric universe, and that is what the majority of the people believe. And then there is the flat earth, which is what a small handful of people believe the earth shape really is. And if you listen to them, they'll constantly say horizontal equals level equals a straight line. And if this is true, then this would be how one would go about modeling a scene in a flat earth. If you have the photographer who happens to be at 6 meters above mean sea level, and I just put an estimate of 6 meters, it might be 8 meters, it might be 7. I showed clearly in my previous video animation that you would have to be over 100 meters above or below to have any significant parallax to make it appear as if the flat earth looked like a globe or the globe earth looked like it was flat for this scene in particular. If the photographer is 6 meters above mean sea level, and again I did a bit of research, and according to Google Earth, the top of this tower is 169.1 meters above mean sea level, then the amount of tower above your horizontal eye level to the top of this tower would be the difference of 169.1 minus 6, or it would be 163.1 meters. This gives you the vertical height of the tower above your eye level. If the distance to the tower is 19.6 kilometers away, then you would use the arctan function to calculate the angle to the top of the tower. I did that and I worked it out to 0.47 degrees above my eye level. Dow Crag has an elevation of 759 meters above mean sea level. Again, if I subtract 6 meters from 759, I'm left with 753 meters for the vertical distance above my eye level. And with the mountain 81.4 kilometers away, again you use the arctan function and it works out to 0.52 degrees above eye level. In this scenario, the tower appears to be lower than the mountain, and that is consistent with the renderings that I've shown of a flat earth with a tower not even attaining the height of the mountain behind it. But as we know, the picture that the photographer took clearly shows, very clearly shows, that the tower is well above the top of all of the mountains behind it. And while I'm looking at this picture, I would like to address the Rayleigh criterion. It means minimum resolvable detail. If we come back to the photograph, certainly looks to me like there's a lot of detail that can be seen. You can see the individual support struts of the tower. You can see mountain ridges behind it. You can see the crags in the cliff face behind it. You can see all sorts of stuff everywhere. So if you can see that much detail, why is there only a small band where ground meets sky where you cannot resolve anything, such as the bottom of the boat going over the curve? Using the Rayleigh criterion as an alternative explanation why the bottom and only the bottom of the mountain is not visible, where it is perfectly explained in a globe Earth, is a logical fallacy. So let's take a look again at the globe Earth model in crayon format. I made a video that showed the math that I was using, and I also had a link to the triangle calculator that I was using, and we can estimate with reasonable precision all three sides of the triangle. We know that the average Earth radius is 6,371 kilometers. We know that there is atmospheric refraction, and generally it works out to 7/6R. So if you multiply the Earth's radius by 7 and then divide that value by 6, you're going to get an Earth radius that is over 7,000 kilometers in radius, and that would be the equivalent of what we see through the atmosphere. The calculations are the same. The only difference is the value of the R that you use. So you add to the radius of the Earth the altitude at the very top of the tower, or the very peak of a mountain. That becomes the length of one side of the triangle. The length of the second side is going to be the Earth's radius, plus the altitude above mean sea level of the observer. And then the third side of the triangle is the line of sight distance between the observer and the object. For the tower, it's 19.6 kilometers. For Dow Crag, it would be 81.4 kilometers. Put those three values into a triangle calculator, and the one that you're interested in is this angle here. The side of the triangle that goes from the center of the Earth to the observer is the observer's plumb line, and a 90-degree angle from that would be the observer's horizontal eye level, and it would be 90 degrees. An angle that is greater than 90 degrees means that you are looking up. Again, if you refer to the spreadsheet that I made earlier, you will see that the tower had an angle above my eye level of 0.4 degrees, and that the top of Dow Crag had an angle up above my horizontal eye level of 0.21 degrees. For the observer taking the photograph, in this case looking towards Blackpool with the mountains behind it, the tower appeared higher than the mountain behind it, and that is why the globe Earth model matches the photograph and matches reality. The last point I'd like to bring up is something that this flat earther kept saying in the comments, that if you just move the camera up or down or zoom in, zoom out, or move forward or backward or whatever, everything changes, and it's just the perspective that shifts, and that's why the tower appears to be higher than the mountain behind it. And in my last video, I showed how you would have to be over 100 meters below mean sea level in order to look up and to see the top of this tower appear to be at a higher elevation than the top of the mountain behind it if it was a flat Earth. I also showed how on a globe Earth, if you go up in altitude and you look down, that the mountain behind it appears to be taller than the tower behind it. The last thing I would like to show is an animation of the observer stepping back a little bit from this point and then moving forward far enough so that tower appears to be higher than the mountain behind it, just like in this photograph. Here I made an animation where I put a yellow sphere where the photographer was was when they took that picture. This is the flat earth model. The water is also flat in this case, but I added a couple of other displays that were not there in my previous video. I added a zoom multiplier. I'm not zooming right now, although I could make a few more animations if I really wanted to, with zoom and tilting the camera up and tilting it down. But in this animation, I was only interested in seeing what happens when you move forward and back, how the tower appears relative to the mountains behind it. You'll also notice that this yellow sphere stays in one position as I'm backing up or moving forward, but you'll see this other object. It's a smaller circle with alternating red and black bands, and that is a measuring stick. If I were to pan down, you would see a green disc above the water, and below that you can't see because that's under the water, would be a red disc. And the idea behind that would be to show that as I'm moving forward and backward on a globe Earth, that I'm adjusting my camera height to match the height of the water. Pavre uses a 3D coordinate system, and right now the flat earth model is keyed to the vertical axis. So all points of equal altitude are going to be the same value. So it's easy for me to move the X and the Y around to appear to be moving forward and backward. But for this one, all I wanted to do was to show what happens to the tower and the mountains behind it. First, I back up a little bit to about half a kilometer, and then I start moving forward again. And I keep going forward until I get to 13, it should be about 13 and a half kilometers. So this 13 and a half kilometers is the distance in front of this point here. So it's off in the water here just before it reaches land. If we compare the photograph, in order to get the tower to appear roughly at about the same spot, the photographer would have had to been 10 kilometers closer to Blackpool. In other words, the photographer would have had to been over here, 9.6 kilometers away from Blackpool. I'm going to insert the animation here. And I really hope that this is going to be the last of this Blackpool Tower series. Thank you for watching. If you like this video and you're not subscribed and you like the content, I would appreciate the subscribe. Feel free to hit whichever thumb button you like, and be sure to leave a comment below. I think I'm going to shift gears and start working on one of those project builds that I had in mind that I've been wanting to do for some time now. It would certainly help with my interest in astrophotography. In the meantime, that's it. Thank you for watching, and I'm going to see you again in another video soon enough. Bye for now.